Okay, so we're back here at Unix, and we have this dupe command, which we talked about last time. Dupe duplicates a. Can somebody tell me what dupe does? What does it duplicate?
That's what it says there. Right? Say copy of the file descriptor.
Yes, it duplicates the file descriptor. Don't no, you can't cheat because if you just doesn't matter. It's not called cheating. So dupe duplicates a file descriptor. Well, file descriptor means like you have an open file and you have a number pointing to it. Now you have another number pointing to the same file. So you have two pointers pointing to the same file. And we did that here with an open file. We made a copy of the file descriptor by simply giving FD that we got from open to dupe, and now we got a FD, and this is a different number now. This is maybe 4 or 5, and that's going to also point to the same file. So if I write to 4 or whatever number I got in FD copy, it'll also go to the file. Fair enough. Now we have a more complicated example. We went over this last time, but we'll just do it again quickly. Where we make a fork, we might as well make a pipe here. We make the pipe, we make a fork, and that means the fork is shared by all the different processes. This is if there's an error, this is the child, and this is the parent, because his default is not, he didn't get 0 for his pipe, for his fork return. So we'll notice the child closes the read side. He also closes 1. Now that's kind of weird. 1 is normally pointing to the screen as a standard output, but he closes it. So now when he does dupe, dupe will automatically return him the next free number, the lowest number that's free. And the lowest number that's free is 1. So now 1, which usually pointed to the screen, will now be pointing to the same thing that PD1 is pointing to. Well, PD1 was pointing to the pipe's right side. So now 1 will also be pointing to the right side. So that means if I do printf hello, you would think it goes to the screen. But it's not going to go to the screen, because the way it goes to the screen is not by saying, please go to the screen, but by printing, by writing to file descriptor 1. Now, file descriptor 1 is usually pointed to the screen, but I closed it and then made it, and then did a dupe and made it point to the pipe. So this hello user will not go to the screen. It'll go to the pipe, even though, because printf is unaware. Printf is sort of oblivious. He just writes to file descriptor 1. But file descriptor 1 is now pointing to the pipe. Any questions on that? Okay, and then the parent process will read from 0. Now 0 would normally be reading from the keyboard. But in this case, since I closed 0 and I made dupe on the read side of the pipe, dupe will automatically return me the next lowest number available. So 0 is now available. So it will be 0 we point to the pipe, to the read side of the pipe. So now I'll be reading, even though I'm using the command read, I'm actually, and 0 here, which normally would be the keyboard, now it'll be the pipe. And this would have been exactly the same if I had written read from PD0. I'm just showing you how dupe can be used to do unusual things here. And put character is just another way of putting a character on the screen. Okay. Oh, I went the wrong way. Now there's dupe Stein. Did I also discuss dupe Stein last time? Dupe number 2, dupe 2. Dupe 2 is just like dupe, except that instead of having only one parameter, the file you want to copy, it has a second parameter, which is the file descriptor you want to create. So in other words, I could write here, for example, the number 7. And then it'll make that file descriptor 1, or whatever I give it, whatever it's pointing to, let's say 1 is pointing to some pipe, or let's say 3 is pointing to some pipe, and I give it 3 and 7 here. So now 7 will also be pointing to the pipe. I'm saying whatever 3 is pointing to, whatever this one is pointing to, also make this one point to the same thing. I don't know. I don't know how in here. So no, you can ask Baba to help. The dupstein function causes the file descriptor file2 to refer to the same file as file descriptor. So that means I can give it. So it sort of like lets me decide what actual file number will be assigned. Instead of it being the first free one, I can say this number should be assigned. Now, what happens if file2 already refers to an open file? In other words, file2 is not, it's 7, but 7 is actually pointing to some file. And now I say make file2 duplicated to make file descriptor 2 duplicated to file 7. So if this one already is open, what's going to happen is I'm going to lose that. It's going to be overwritten. It's closed first, and then it's overwritten. So again, if this is referring to some other place, then I'm going to close it, and then this will now refer to whatever this is referring to. So that's what I'm going to do, I think, in the next example. Yeah, so look what I do here. I have my pipe. I have my pipe, I have my PD and my, okay, and I say pipe. I create a pipe. I have a single pipe, I do a fork. Check for errors. If I'm the child, okay, I'm the child. And I have a single pipe. Matkonet. Matkon. So close PD of 0 means that I'm going to close the pipe. Then I'm going to do dup 2 with the right side of the pipe and 1. So wait a second. 1 is already pointing to what? Everybody together? What's 1 pointing to?
Pipe.
No.
The standard output.
Standard output. 1 is pointing to the standard out. Yes. Tiny piece. תגיד לי, בבא, לעשות קטן מאוד. בבא, קטן מאוד. Okay. So 1 is pointing to the standard out, which is the key, which is the screen. So what I'm saying is stop it, close 1, and make 1 point to the pipe now. So that means, again, when I do print hello user, it's going to go to 1, which is also the pipe. So I didn't have to close 1. It automatically got closed and then opened up again to be pointing to this, to whatever the pipe was. And again, here I did dup 2 with 0. So 0 was pointing to the keyboard, and I closed the keyboard and made the 0 now point to this pipe. So when I read from 0, I'm actually reading from the pipe. So I'm just showing you that dup 2 is a little bit like saves you some work. Okay. Diverting the standard output to a file descriptor. Standard out of the child process is diverted to FD1, and standard in of the parent process is changed to FD1. So let's see what we do here. Again, we make our pipe, we make our fork, we check for errors. We now, in the child, we close the read side because he's going to write. We again say dup, and we print hello to the pipe, and we close the pipe. Now the father closes the right side. He's getting ready to read, and he reads from, well, first, before he reads, he makes 0 point to the pipe, and he reads from the standard input, and he reads actually from the pipe because he's writing using get string. Get S is get string. He's reading from the pipe, but he's using get, and get only reads from the keyboard, but since the keyboard is actually pointing to, the 0 is actually pointing to the pipe, it's going to work. Okay, that's pretty much the same as the previous example. Now here's an interesting question, which one of my students asked me a few years ago, and so I gave him this answer. The question is, just checking if people are there. Question is, if I close the standard out, how can I ever write again? It's how I get one, I close one, and I close two. So how am I going to write to the screen ever again? I lost it. So since we may lose the access to the screen of the keyboard when using dupe style, right? If we do dupe 2 and we use give it 1, then we're going to lose 1. So it is interesting to see how we can regain access to the screen. So here's how you do it. So first of all, let's just make a file called file1, and we'll open it. And we open it for create, read, and append. Oh, sorry, write and append. And then we say, we check for errors. If we didn't get a proper file descriptor, if it didn't work, always check for errors, because otherwise you won't know why your program didn't work when you do get an error. Now, if dupe 2, here I should also check for errors, but whatever. If I don't always check for errors, but it's always good. Dupe 2, FD to FD1. So that means I'm going to now lose FD1. I mean, I'm going to lose 1 because I may use dupe to make FD to make 1 point to whatever FD was pointing to, which is my file. So now if I do printf hello, I won't get anything. And if I do flush, make sure I won't see anything. Really, I wrote to the file. This is printing because the 1 is going to the file. Now I close 1 because I want to finish writing to the file. If I open a file for write only, open will get an FD1 also. If I do another open, where I do an open for write only, I'll get FD1 again. But it's because FD1 is done, it's finished. Now I want to be able to print to the screen hello world. How can I do it? I could use 2 because 2 also points to the screen. Standard error. But I want to use standard out to point to the screen. How can I do it? So I have to do like this. FD open. Which file do I want to open? The device, TTY. TTY is the screen. Teletype it stands for. Open it for write only. It must be write only because the screen can only be opened for write only. Can't read from the screen. So I open it from write only. And now I get FD. And what is FD? Well, I just closed 1. So the operating system is going to give me 1 as the next free file descriptor. So now when I do print F, 1 is pointing to the screen. And this will work. So I'll print F, D for decimal, the FD, the number that I got, just to prove that it's a 1. And then I print F hello world, and that I will see. The hello file will still be in the file. That was just to show you that this printf didn't work. I mean, it worked. It wrote to the file, but didn't write to the screen because I closed 1. Somebody want to make, now is a good time to make a question or a comment. Okay. Yitz, you have a question? Yitzhak? No.
I do not.
Okay. Wait. Wait waits for a process termination to occur. The wait function suspends the execution of the current process until the child is exited, or until termination signal. If a child, okay, so let's see an example before I go on here. If I would run this program without this wait here, notice there's a wait here. I'm just make a fork and I do 2 prints. What's going to print first? Child is running or child is terminated? That's a question. What will print first? Child is running or child is terminated? Which will I print first if I don't have this wait here? That's just a regular program. I do a fork and I print and I print.
Child.
Okay, any other answers?
Well, says father will wait here. Well, without it.
No, without that.
No. The father will go, then the child.
Any other answers?
The child will go, then the father.
Any other answers?
Both go
Compile
south.
error.
Oh, we won't be able to tell which goes first. Perhaps it depends.
Exactly. We won't know. It is indeterminable which one will go first because they're running in parallel. I don't know which one will print first, whichever one the operating system gives more CPU time to. You know, once this fork hits, there's no, all bets are off. I don't know who's going to go first. So that was a problem. What if we want to synchronize our processes? So to do process synchronization, we need to wait. The father can do whatever stuff he wants to do in synchronization. And then he'll come to this wait. In other words, imagine that there's other lines of code after this brace and before this wait. There could be. Doesn't have to be, but there could also be. In this case, I didn't write anything. And then at a certain point, the father says wait status, and he's going to wait for the first son to finish. Now, notice if he has many sons, he will just wait for the first one, and then he'll go, child has finished. So that wait is useful in, I don't want to print child is terminated and be wrong. If it would print first, then it would be wrong because maybe child is still running. So I want it to reverse this, so he has to wait. Now the parent can't wait for the father, but the father can wait for the parent. And now what about this status? This is just the way the wait function is written. It requires an address of an integer. So I made an integer and I gave it the address of the integer. So for our purposes, really, it's just required to write it that way. But actually what it does is since it has the address of the integer, it can actually put a value in that integer, in the real integer, not a copy, but in the actual integer as a reference to it. So it will actually write into the integer some number, which is the status, which is whatever status the child finished in. If he finished successfully or, or with a failure or something. The exit code of the child. Do I have this other thing? I don't think I show you here. So I'll just tell you, there's also a command called wait PID. Can anybody guess what wait PID means?
Maybe wait for a specific child. I don't know.
Exactly. Wait for a particular child. I can know the PID. Since when I did this fork over here, the father got the PID of the child. I can store it and then do wait PID. And then this function will have two parameters. The first one being the PID that I want to wait for. So I can wait for a particular child if I have many. If I had several children, I could do several waits. And then each one would wait until each one would wait until one more child died. So maybe that's what I do here. Here, I save the PID of I do a fork and I save the PID number in a child1 variable. It's a type PID type. And I write child is running because I did a fork, so the child is running. This is if the assignment, first of all, I assign it to child1, and then I also check if it's equal to 0. So if it's equal to 0, which means it is the child, then child1 is running. Else, I'm the father, and I make another child. Child2 is running. Else, I'm the father, and I do wait PID status. Now, I don't know which one finished first. I do know which one finished first because wait also, in addition to putting a status here, it also returns the PID of the process that it succeeded in waiting for. So it could either be the value of child1 or the value of child2. There's two children running at this point when he does wait. So whichever one I got, I'll write PID equals, if PID equals child1, then child1 terminated first. Otherwise, child2 terminated first. So that's an example of how I can know which child finished first. And I can do the opposite, the last child to print first by simply doing two waits. See, I do a wait and then a wait. And then I check the second PID. I check the PID that got assigned second time. And now I know which one finished last. I could do that. So, and I told you also I could wait for a particular one. Okay. So let's go on. There is a command called execl. And execl allows me in a program to execute another program. I don't know if you probably never did that in C++, but you can. And here we're doing it in C. You're executing another program. As I can write another program, compile it, and put it in a certain path. And I write the path here. And I put the argument. I put the, well, let's see what the argument is. Wait a second. It's not actually a system call, but it's kind of like a system call. So it's part of the family of exec functions. There's several. There's execl, there's execv, there's execvp. There's different ones, but they're all very similar. It replaces the current process image with a new process image. In other words, the previous process disappears, and now I'm just this new process. The initial argument for these functions is the path name of a file which is to be executed. That's the path. And then here I'm going to write notice there's a 3 dots here. That means that it accepts a series of numbers. An infinite series, however long I want, of arguments. And it has to be a null at the end in order to know it's the end of the list of arguments. A null, of course, is the ASCII value 0, so I can just write a 0. Execl expects a complete list of the commands arguments you want. So let's see an example. Here's the most basic example. The files in the directory are, and then I do execl bin ls. Let's say that's the location of where ls is. I have to write the word ls here and again here. That's the program I'm running, comma. The name of the command that I'm running. It could be different, you see, because it could be a link, you know. It could be that there's many links to this ls, and I could write a different one here. Anyway, ls is the name, ls bin is the path, and then the parameters. I want to give it -l. I want to do ls -l. I want the long form, the list form. I want it to tell me all the data about the file. And then a 0 is obligatory to have at the end of the list. Now it'll run this command, but this third line will not execute, because once I ran execl, it ran ls instead of my program. It's sort of like I jumped over to ls. I ran ls. When ls finishes, it has no idea how to come back. It does not come back. Here's an example with exec v, which is similar to execl, but it takes a vector, and you'll see that's more useful. Execv, I can make it a vector, which is just an array of arrays. It's a 2-dimensional array of characters, 1,000 long. That's how big I made it. I could have made it different size. And then I define it right away. By the way, this is 1,000. This means it can point to 1,000 strings. And here it's pointing to 1, 2, 3 strings, maybe 4 strings. So that's ls -l on the function, on the program a.out. Files in directory are, and now what do I do is a complicated thing here. I do fork, first of all. And I say, if it's equal to 0, that means I'm a child. Only if I'm the child, then do the command execv, the location of the file I want to run, which is ls, and the array that has all the information that I want to use, this array. So it includes the ls, even though you threw $, you know. Okay, so execv is just like execl, except I create this 2-dimensional array. And we'll see that's useful because I can then, I don't have to hard code it. I just put an array here and I can change these values. Now it's important that I let the son do this. Why is that important? Why I make a fork before? Because we had that problem that we said this line will not print, will not execute. Now what I do is I make a child. Now we're going to start to see why we make children. We make children in programming here because we're going to do an exec on it and let it run some other function. And I'm not going to die because I made a fork. Only the child is going to finish his thing. When the child finishes, I'll find out about it. So before this wait or after it, I can write a lot of code to do whatever I want, and it'll run in parallel with the child executing this. And even though I did an execv, which does replace the process image, it doesn't matter because he's going to be able to take that image with him wherever he goes. I'm sorry, because sorry, I lost track of what I was saying. If the fork equals 0 and the child, this child will die after he finishes executing, but the father will go on living. That's why I made a child. The father didn't do see, in this one, the father did the exec. Here, I made a child, so he'll do it, and then I'll just find out when he finishes. Now, there is a shortcut to that, and that's called system. Here, you just write the command. It's much easier. You don't give it the path. You don't give it any special nulls. Just write what command I want to do, and you give it the parameter. I want to do vstat with a space 1. So without even knowing what that is, it's virtual memory statistics or something like that status. Without knowing what that function does, I have a question. Should hello be printed? And if it was like execl and execv, it would be no, it wouldn't be printed. But that's the difference. System returns. It does, I don't have to make a fork. It essentially makes a fork for me, right? It makes a fork for me, makes a child, and lets the child run vmstat, and then waits till it finishes, and then comes back. So system is like a another program, another function that's like makes your life easier, but don't use it in the lab that I'm going to give you. Okay, popen. Popen is a funny command that combines some things. Essentially, popen combines several other system calls. It creates a pipe, forks a child process, and to run a command. The output of the command is then returned via the pipe and is pointed to by the pointer returned by the calling popen, by the call to popen. P-close waits for popen to finish executing. So it's not going to actually close anything. It's just going to sit there and wait. So if the policeman, well, whatever. Okay. Closes, waits for popen to finish executing. Again, it opens, it creates a pipe, forks a child, so like we've been doing all along, runs the command in the child, but it also does, important thing, it returns the output of the child to the pipe that it created, so that the user can use it. So for example, here's the way you do it. It would take a command like ls-l and a pointer. We'll see. Let's see an example of using it here. So here's popen. This is my last. Oh, I have one more example. Okay, here's a simple example. Output is apples are tasty. Because what I did was I did popen. And I ran this command. Said. So what is this second parameter? It's to tell you whether it's for read or write. Am I reading from the pipe or writing from the pipe? So it returns to me this pointer, this pipe pointer. So then I can do printf, which means apples are tasty, print it to where? Not to the screen, but. The F means file, print file. So it'll print to the file p, not as I can specify here, kind of like a write command, where I'm writing to. So I have to use fprintf though. I can't use a write because this is a special return value of that. As you can see, is a file. It's a file which is only with the f functions works. It's not a regular descriptor. It's a file pointer. So I have to use the fprintf. So I open this. I open a pipe with this command, and then I tell it. Then I say, write to this pipe. Apples are tasty. So it writes apples are tasty to this pipe. Then I close to tell it I'm finished writing. Now the pipe is fully filled and done. So over here, though, the p open, now he sees that it's ready. He's going to run the command. What is he going to do? He's going to read out from the pipe and send it to this command, this sed. Well, this sed we learned before is a switch from A to capital A globally. So it's going to check all the A's and apples are tasty and make them big. Anyone want to ask something about that example? Okay. So now we have another example of p open, a little bit more complicated. And now, okay. And now what am I doing? I'm making a buffer. I'm making a p file, a pipe file pointer. And I'm opening. I'm doing p open. And this is the command I want to write. ls minus l of p open 1. That's C. So you see here that I said, well, p open 1 is in this directory. Well, that's probably likely. It doesn't have to be, but anyway, I mean, it won't work if it isn't. So I do ls on p open 1. That's C. And on the file temp C, because you can do ls and give it a bunch of files or two. So I did an ls on p open and this, and I did it reading this time. That last time was writing because I wanted to write the result of this sed into the pipe. Now I want him to read from the pipe. That's interesting. What does it do? Wait a second. Okay, so again, I open this thing and I open it for read. Well, we'll see why in a minute. Why did I open it for read? Because I'm printing to the standard error, this ls command failed. That's if it returned me null. In other words, if this returns null, it'll print, but, and then exit 1. Else, so while fget, you see, in this case, what was I trying to do? In this case, I was trying to write to the pipe the output of this command. Or write to the, I was trying to write to the screen, actually. So it's a write. In other words, I'm writing into the pipe, and I'm reading, and then I'm writing it out to the screen. So maybe this W, maybe a better way to think about it is like this. This W means I plan to write to the pipe. And this one means I plan to read from the pipe. I plan to read from the pipe. Well, that makes sense because this is ls. ls produces something. So I'm going to read from it. And that's exactly what I do over here. I do fget from the pipe, from pfp, into buffer. So I'm reading from the pipe into the buffer. And then I print the buffer. So again, this R means, do I plan to read or do I plan to write? Here, I plan to read what this output is. In this example, I plan to write to this. I'm going to give it output. See, I did a printf. I gave it output. I'm planning on writing to this. Here, I'm planning on reading from it. Okay. That's it as far as the lecture of Unix for today. I want to now do the lab. We'll spend more time on the lab. Because I want to show you how to put all this together in the lab. First of all, there's lab 3, which I don't know if I didn't really show you much about. I can also did this, I want to show you what you're gonna have to do for lab 4. I didn't yet post lab 4, but lab 4 is gonna be to write a shell. So let me stop this share and stop this recording.